Hello, everybody. Welcome to Physics 1403 Stars and Galaxies. I'm standing here next to a picture courtesy of our friends at NASA called the Hubble Deep Field picture or the Hubble Deep Field photograph. And what you're looking at here are literally hundreds, if not thousands, of different galaxies. This picture took about a week to take, and they just took Hubble and they just aimed it at at an area of deep space. They didn't aim it at an area where we know something is at, or there's a star here, or a planet here, or a known galaxy, or something like this. They aimed it at what would appear to the naked eye to be blank nothingness. And this is the picture that they got. It's been described as one of the most important pictures in NASA. This demonstrates just how many galaxies are in the universe. And just to kind of give you an idea of what we're really talking about here, I have a penny in my hand. If I was to hold this penny up, just like this, and look at this penny, that picture would fit entirely behind Abraham Lincoln's eyeball. This isn't even the whole penny. In terms of what the night sky looks like, what the universe looks like, we are populated with billions, hundreds of billions of galaxies that each of them is populated by 100, 200 billion stars with, how many planets and comets and binary systems or whatever there is. But this picture demonstrates just how big our universe is. All of these are galaxies. There's not a single star there. So what is a galaxy? Well, a galaxy in its easiest, shortest terms is a collection of stars, of gases, of dust, of other things, planets, various other things, including dark matter, that are all bound together by gravity. Gravity is a hugely powerful force that, in essence, the range of galaxy is unlimited, of gravity, excuse me. In essence, the range of gravity is unlimited. And, and while it does get weaker at distance, um, it's still pretty impressive force. All right, so right here, these are some just different types of galaxies. As they've gone and as we've been able to image a lot of these different galaxies, we realize that galaxies have certain structures to them. All right, and so a couple different shapes that have come out, and you see the most frequently, is the elliptical galaxy. The elliptical galaxy is going to look a little bit like a blob, and they have different ratings on this elliptical galaxy. And I realize that some of this might be because we're looking at it oblong, but how we're looking at it. But the more maybe some of them are a little bit more cigar shaped. All right, if they're cigar shaped enough, they may even be called a ventricular galaxy. All right, so they just kind of have the blobs to kind of being the spread out blobs. Okay. You have the spiral galaxies. The spiral galaxies can have 2 arms, they can have 4 arms. I don't even think there's a limit to the number of arms that they can have, except that what we do see is that spiral galaxies have a little bit different evolution than elliptical galaxies, which we'll talk about in a different video. So these spiral galaxies, these arms are caused by a couple different things. Part of it is density. The density piles up. This galaxy is spinning. All galaxies spin. And as it spins, you have matter that begins to pile up. That's called a density wave. And so that matter begins to pile up. And so these arms are from where that matter has, particularly gases, have piled up and kicked off uh, stellar birth. And so then you also have some that, and so the more defined the arms are, then you'll have like a spiral galaxy, an SA or an SB or an SC, depending on how defined the galaxy arms are. Milky Way and our closest, one of our close neighbors, the Andromeda Galaxy, are barred spiral galaxies. And same thing, you have this, maybe you have a not well defined, that may be an SB0. You may have a very well defined, that might be an SB1 or SB2, all the way up to like an SB3. And the difference between these galaxies is that this bar structure here in the center. Bar structure galaxy, that bar structure is probably the result of the accumulation of dark matter and of dust. And so it kind of gives that a little bit of a star bar shape. And then right here, these are the irregular galaxies. Irregular galaxies are probably subject to a lot of external forces. And so instead of forming some sort of structure like these other three, their structure is, they're all gravitationally bound to each other, right? But that structure is, well, I guess that structure is just less structured. Okay, there's an irregular galaxy that is Canis Major that is very close to the Milky Way. And so the Milky Way is actually ripping it apart and stealing stars and dust and other things like this from it because it's so close to us. All right, and so you have these different galaxies in their basic overall structure. I want to take a closer look at the Milky Way. This is our Milky Way, and this is the information here is the result of years and years of observations through telescopes, whether they were in orbit or they were on the surface. And so, in fact, if you go out to the night sky and you look up at the night sky and you see the kind of looks like this little milky splash, that's where we get our name, the Milky Way galaxy. All right, well, that's because we're in the middle of this bulge. We are right about here. Okay, so we are quite some distance away from the Milky Way. Here's the sun. We are about 8,000 parsecs from the center of the Milky Way galaxy. And at the center of our Milky Way galaxy, there is a supermassive black hole called Sagittarius A star. Gets its name because if you go outside and you find the constellation Sagittarius, if you turn and you look at it, you were looking at the center of our galaxy. You were looking towards the center of our galaxy. And so anyway, so we're about 8,000 parsecs, which means the total distance across our galaxy is well over 25 parsecs across. All right, so this is what it would look like from the top. Here's that bar structure. Here we have two very well-defined arms. Those arms are blue arms because there's a lot of type O and a lot of type B stars in it. And they are super hot. They glow with the bright blue, but they're very short-lived. And because they are short-lived, they often don't get that opportunity to travel very far before they've faced death. All right. The central bulge here in the center, here's it from the side. You can see right here, we're in the arms. This central bulge here, it's going to have a lot of older stars in it. Yes, it's going to have some active starbursts. So there's going to be some type O, some type B stars in there, right? But there's going to mostly be some older stars in that area because this area is not as active with star formation. And the reason is because a lot of the dust is being slammed together along these spiral arms as matter begins to kind of pile up. Right? So we have that central bulge here, and then we have the arms, right? And then we have a halo. And this halo are older stars. They are very spread out, and there is not any O or B. There's not really any active starburst going on in this halo because everything is spread out so far. You do have a couple globular clusters. In fact, one of those is probably Canis Major. That's really sort of a dwarf galaxy. And our galaxy, Milky Way galaxy, is part of a larger group called the Local Group. It's a cluster of the Milky Way galaxy, the Andromeda galaxy, the Large Magellanic Cloud, and the Small Magellanic Cloud, which are only visible from the southern hemisphere, and and several little dwarf galaxies that globular clusters and everything like this. And so we're all of these stars are gravitationally trapped together. And by the way, there's kind of a misconception that we're all trapped by the gravity of this supermassive black hole. We are trapped by that gravity, but we're also trapped. Every star, every nebula, every rock, fleck of dust, whatever is in this galaxy is contributing its mass and thus its gravitational attraction. So we're not just held by the gravity of Sagittarius A star. We're held by the gravity of the stars in general. And so we're all held together by each other's gravity, not enslaved by a single, single heavy supermassive. And it is supermassive, by the way. It has a mass of about 4.3 million times the mass of our sun, making it easily the heaviest object in our galaxy. Okay. Galactic clusters, like I said, the local group, they are also bound by gravity. We are all bound together by gravity to each other. And even our clusters, and we're what they call a poor cluster. We don't have a whole lot of metals in our cluster. Rich clusters have a high amount of metals, and it's kind of a subjective, determination there, but it's not like there's a hard fast number that I'm aware of. And so the rich clusters are less common than poor clusters. But anyway, so our local group is a poor cluster. We just don't have a lot. Only about 1% of our mass are actually metals. The rest of it's mostly hydrogen and helium. Anyway, and so our local group is part of a supercluster. And it's the Virgo supercluster. And that cluster just kind of seems they're sort of orbiting each other, but they don't really necessarily seem to be bound by gravity. They're just more because the universe is not evenly spread out. Okay, the mass of the universe is very randomly distributed, but it is not evenly distributed. And so you have these superclusters, and so that kind of gets us to the structure of the known universe. All right, so so this is a galaxy. Now, by the way, we have a problem when it comes to these arms, and I want to show it to you. This is the problem. Okay, so I want you to imagine if we have three objects here that once upon a time are all in a nice, perfectly straight line. Okay, and that you could like almost take, if you had a big giant laser, you could just like zap and hit all three of them right there. And after a given amount of time, this one has moved a certain distance, and all three of these have moved the same distance. Okay, and so now instead of being in a straight line, they're in a slightly curved line. After another set of time, same amount of time, everything has moved the exact same distance again. All right, so now this object, which was down here, is now almost halfway around the whatever is this the pivot point for everything, the center of this galaxy or something like this. Whereas this one is only about a fourth, and this one is less than a fourth, considerably less than a fourth. All right, so you can see that that line once again is becoming more and more curved. If we go the same amount of time, time number 4, so for 1, 2, 3, 4, you can see they've all moved the same amount of distance, but this one has, because the circle it's orbiting in is smaller, has gone almost 3/4 of the way around this central pivot point. Make sense? By the way, this is where some of those galaxies, those arms come from. Okay, is that structure that we're seeing. But there is a major, major problem with this, and I want to see if I can explain it. If our galaxies were solid, okay, if our galaxies were solid, then everything should be in a straight line the whole time. Think about a record or a CD or a disc or a plate. You go to the circus and the clown's up there with the plate going on the string, right? Everything, if you were to draw a line from the center of that plate to the outside of that plate, no matter how fast he spun it, that line would be straight, right? If you happen to like old vinyl and you have a scratch on your vinyl, that line doesn't change shape no matter how fast you spin that record around. And so that tells us, because that's not the structure that we see here, that our galaxy is not a solid shape. Okay, we knew this. Our galaxy is made of 200 billion stars plus other stuff and things like this. So yeah, we didn't expect it to be a solid. What we expected was for objects to follow Kepler's law. And Kepler's law says that, and I'm paraphrasing this, okay? Kepler's law says that the closer that object is, because everything's going to be an elliptical, that objects that are closer to the center here have to be moving faster because otherwise they'd fall into that gravity cell, that center of gravity. All right. So for example, if you look within our solar system, uh, Mercury on any given day travels much farther than the Earth. If we were to look at its velocity is considerably higher. Well, that makes sense because objects avoid falling into each other. For example, our moon does not fall down and hit the Earth, even though it is technically falling. And Earth doesn't fall into the sun because in addition to gravity pulling this way towards the sun, we also have latitude. We have velocity latitude. And so in essence, what happens is as we are traveling, we're going and we are falling, but we keep missing the sun. So if we were closer to the sun, we would have to be traveling faster to avoid falling into the sun. So that's, and Mercury would have to be traveling even faster. Okay, this is Kepler's law. Kepler's laws of planetary motion, and that's what we expected to see when we look at a galaxy. The problem is that is not what we see. We see that essentially objects are traveling at the same speed instead of traveling at different speeds based on how far away they are from the center of the gravity, from a Sagittarius A star. And by the way, we see this in other galaxies as well. Any other spiral galaxies, we see a similar structure. We see where they are all traveling about the same speed instead of the ones that are closest to the center of the gravity having to travel faster to avoid falling in. All right, well, what if there's other gravitational influences? I said that a galaxy is not trapped gravitationally to one point. They're all sharing that gravitational attraction, so they're all attracted to each other. Well, when they do the math, and I'm going to spare you the math, when they do the math, the problem is our galaxy is not heavy enough to support all of these objects moving at the same speed, especially these distant objects. These distant objects, there'd have to be something out here equalizing the gravitational attraction to in here in order for these guys to still be moving at the same speed. So there must be some form of what they refer to as dark matter. And what's more is it may be 85% of the matter in our galaxy. And they call it dark matter because we can see its effects, but we can't see it. It doesn't seem to interact with light. And because we can't see it, we can measure it indirectly. We can measure it by the effects of it has on gravity. Same thing, when you start looking at galactic clusters, such as the local group, or you start looking at some of these others, you see that same pattern that begins to form, where these galaxies are spinning around each other, and they're spinning way too fast for them to just be accounted for the visible matter. So we must have some sort of matter, exotic matter that we don't know what it is, and we haven't figured out a way to interact with it. So now the question has become, well, what is it then? And there's a couple ideas behind it. One is that it's some sort of exotic matter that we just haven't discovered yet. And we're still trying to figure out what it is, okay? One is that it could be a bunch of neutrinos. So neutrinos are very, very light, highly energetic particles. For example, neutrinos are the actual energy whenever a star dies, it goes through that supernova process. Neutrinos are actually the forces that push that new matter, all of that explosive. It's not gas pressure, it's neutrino pressure that pushes it out into the interstellar medium. And so we know that there are neutrinos. We just don't, the problem is that neutrinos, to the best of our knowledge, don't clump up. They're found as individual, highly energetic, barely interact with matter particles that are just zipping through the universe. We're being bombarded by them all the time, and we don't even notice. Okay, so that one may or may not be very useful as an idea. Maybe, and there are neutrino hunters. There are people out there trying to find neutrinos to see if they can't figure if that's what dark matter is. Another possibility is something that astronomers and astrophysicists refer to as machos. Machos are massive, sorry, machos are massive, compact halo objects. Remember that our galaxy is surrounded by a halo, and that halo is outside of the disk where the arms are, and so you can see why they might think, well, what if there's a bunch of objects there that we just haven't detected yet? Think rogue planets. Think dead stars or failed stars like brown dwarfs. These massive objects that don't interact, they don't reflect a lot of light, we're making them very difficult to detect. So that's one possibility, is that we have all of these machos out here and we just haven't been able to find them yet. Rest assured, they're looking for them. The problem with this idea is that that's a lot of machos for us not to have found. Okay, that's a lot of dead comets or rogue planets or even dark nebulae and dust and stuff like this. That's a huge amount of material out there for us not to have been able to find it yet. But anyway, so that's one possibility, is that we're looking for a bunch of machos. The other possibility is we're looking for a bunch of WIMPs. WIMP stands for Weakly Interactive Massive Particle. This is some sort of particle that we have not identified, some sort of exotic particle, exotic form of matter perhaps, where it is very heavy, but because of its nature, it just doesn't interact with light easily. And so this is what I was talking about with, like, there's some sort of unknown subatomic particle, some unknown, even something that's like the size of an atom or something like this. And they're hunting for those. They're having to hunt for those. They're using big giant detectors full of pure crystal clear ice to try to see if there's something that's going to interact with this device, to see if we can't find these WIMPs. Right? But as it stands now, we don't know. We really don't know, other than, yeah, there's something out there, and that something has mass. But we really don't know what dark matter is. And I would imagine the first person who can actually prove what dark matter is probably going to take home a Nobel Prize, a Nobel Prize in physics. So there you go. Maybe that could be your, I don't know, senior paper or something. All right, this is what dark matter is. And so there we go. That is what a galaxy is. It is, yes, it is a ball, a bunch of stars, but it's also got a lot of dust, and it's also got a lot of gases. Um, and the reality is most of its mass is actually dark matter that we can only detect indirectly. So there you go. That's what a galaxy is. And so I'll see you next time. Until then, happy star hunting.